Whenever you're ready, Harry.
Yes, I'll start now.
Okay.
Hello everyone, good evening. So I'll be talking about the paper review of identifying productive working patterns at the construction sites using the BLE sensor networks. Basically, like BLE stands for Bluetooth Low Energy Sensors. So the abstract of the paper says like to improve the construction management, there's continuous research going on for tracking workers and resources on the construction site. So in this paper, they use the Bluetooth low energy networks to track the movement and the location of workers. Later, the data was analyzed to evaluate the workers' performance, and it showed that the location accuracy of this sensor is in the range of like 5 to 10 meters, depending on the positioning of the receiver gateway. Again, the data was analyzed with the artificial neural networks to identify the working patterns in relation with the working area assigned. Moving on to the introduction, like we always know that the management of time, resources, and manpower in construction industry are the key factors which has affected the productivity. Increasing the productivity and safety has always been the main motivation or the main reason for the research related to the location tracking. We also know that the construction sites are usually large and it's very difficult to track someone or the people or the resources in the site. So there are various tracking methods used, um, such as radio frequency identification, ultra wideband method, and the cameras as well. But the method used to track depends on the type of site or the design of the construction project. So in this study, they have used the Bluetooth low energy sensors, which collects the data of position and time leading to the interference of the moving speed, as well as the direction of movement and the footprint of the certain areas where the receiver gateway has been located. So as you can see in the diagram, this is the receiver gateway and this is the tag or the BLE sensors which is used in sites or in the study. So the measured data of a site of 50 meters by 50 meters with around 20 workers for weeks can take up to several terabytes. So using this data, different like you can evaluate or analyze the working pattern of the individual worker with reference to the abnormal movement of workers as well. This also helps us evaluate the productivity with reference to percentage time spent in assigned area as well. As you can see in this diagram, like how this whole thing works is you have tags which are attached to the equipment or the labors or which is placed in the site somewhere, as well as you have boundary conditions which have been given by these receiver gateways. So the signal is transmitted to the gateways and the gateway uh, again transfers the signal to the Wi-Fi router, which again makes sure that the data is transferred to the cloud and it is monitored on computers or any device which is feasible for the project managers, and they can make the decision with the help of the data. So the basic principle is what I explained just now, and the project, like the study was made into 3 different phases, uh, where it included phase one phase one was done to ensure that the entire system is working. So they had to make sure that the pairing tags with the the tags is paired with the gateways, and the gateways are able to send the signals to the routers, and this data is again transferred to the cloud, and also they had to make sure that the boundary conditions or the boundary design and layouts are um, working as required. And the second stage was done to adjust the gateway router location with the available power sockets or power sources, and also it included the strengthening or to make sure that the accuracy of the location is near to what is it actually in the real world. So they had to work on the signals as well in the second phase. And the third phase, the actual tracking of the workers to generate the real data was used. So you can see this is one of the gateways which is mounted. Sorry, this is one of the routers which is placed in the construction site, and this is one of the gateways which is placed on the ceiling because of the obstacles in the ground or something. And also this is one of the tags again in the construction site. So this is what was done in the phase one. In phase one, the square grid test was done to check the accuracy of positioning. So the gateways were placed in four corners, which are 5 meters apart, and the data was recorded up to 7 meters by 7 meters of square. Um, Apart from these, the greatest, they perform the tracking studies as well in the phase one to check if this can hold good in the construction sites as well. So yeah, the results. Okay, sorry. The results of the phase one showed that the positioning was always within the gateway boundary. As you see, these are the gateways, and this is the positioning which is within the gateway boundary, and the error of positioning or the location tracking was up to approximately 1 meter. And these results proved that this method can be implemented at construction sites as well. So um, they moved on to the second phase, which was the test was conducted at the construction site. This gives us a chance to look into the real suitability and also the challenges that might arise in the site while using this method. The same system was, and they they copied the draw floor plans, which are the CAD files, were imported into the online platform. The gateways mounted at different levels, and also the different levels because it was a 5-story building. So they kept the gateways in each level, but they had to keep around 11 gateways in the ground level as more number of activities were going on in the ground level. And also the tags were mounted on the floors during the system testing and the signal strength optimization as well. Yeah, the results from the phase two showed that the time resolution of data acquisition for the system was set up to 3000 milliseconds. Initially, initially they had to do the adjustments for the signal strength, as the mapping which was done was had showed a great error like up to 10 meters. So to improve the positioning accuracy, the transmission strength of the tags were reduced. They also, by doing that, they achieved to reduce the error up to 2 meters approximately, and the response time was reduced to 5 seconds as well. So based on these results um, that was obtained in this phase, they could also conduct the next phase, which is tracking of workers or the productivity. In third phase, again, it was conducted in the construction site, but in this case, the individual workers were provided with the tags, which was they were supposed to hold on to when they're working daily, and they received the data, which was analyzed to evaluate the worker's performance, and the data analyzed the data was analyzed to determine the patterns in the behavior, which you can see in this diagram. The the productivity charts were made with the help of this data, and also it was compared to the uh, assigned area and the time the workers were supposed to work. So in this diagram, you can see that the path or the data which is collected from the tags. So if you see the darker spot, it means to say that at this point the gateway received the data for a longer period of time, and same with the other tags. It's just the different labors working in different levels as well. This chart shows that these charts help with the productivity analysis, because this shows the percentage of signal from the assigned area for each labor. So if you say X2 spent around 82% of his time in that assigned area, and if you, I mean, as a project manager, you'll know that it would take up like maybe 5 hours for him to complete the work, but he stayed up there for 8 hours. So definitely, you know that it is underproductive work. So you can analyze using this charts if the productivity as well. And this um, graph shows the path of workers who have moved around the site for a certain period of time. So it's just the tracking of the movement of labors. There is again the tracking of um, labors in assigned areas, again for various activities. So since we track the real workers and the heat map is created, like you saw in these diagram, in these images, and also the data was evaluated as we discussed just now. And the study concludes that the improvement in construction management includes better location of manpower and managing the safety as well. Tracking the location of the workers in construction site is a useful method to achieve it. The results have shown that this system is also suitable to track the location of workers. Based on the design of this network, the accuracy to be quantified within 5 to 10 meters. And the results also showed that the location tracking with the help of pattern recognition methods can be used to correlate worker movement as well as and classify the productivity of each worker. That's it. Thank you, guys.
All right, thank you, Harry. So, quick question. What are the potential limitations of applying this Bluetooth-based indoor localization?
I mean, like the limitation which I see is like you might have some obstacles like which might reduce the signals or transfer of data, so you might not be able to get the full data sometimes.
Okay, and also I noticed that the coverage. So here's the thing. I do have maybe not the same Bluetooth system, but I do have a Bluetooth indoor localization system in the lab. And by the way, if you guys, whichever team wants to loan it for your team project, you're welcome to do that. Last year, actually, a group loaned the Bluetooth device, and they use that in the stadium, and they basically did some experiments. One thing we noticed that was the coverage of Bluetooth signal is limited, and so we're talking about effective tracking. It's very confined, a small area, and like Harry mentioned, also it can be affected by the occlusion. But meanwhile, the Bluetooth device is kind of expensive. The one that we use can track up to, let's say, 2,000 square foot. We have the 3 base station that is sending out the Bluetooth signal, and we have 5 trackers. That system costed us more than $3,000. So what is your opinion? Not just Harry, but everybody. What is your opinion? Like, this looks very useful technology, but in terms of the variability, like how to make it variable, what are your suggestions?
One thing, a lot of people's phones have Bluetooth, so possibly using
Yeah.
that to bounce off like a mesh network to get results to the tracking center.
Mhm.
Okay. What else? Anybody?
And we have Bluetooth in our phone, so we can use the Bluetooth in the phone.
Yeah, but that's different. For this research, they do need to build the infrastructure. So what, Junyi, what you were talking about was the infrastructure-free method. And I think we discussed a little bit last time. Remember, NIST had a computation in 2018, and they required people to use the infrastructure-free method. But the winner, remember that their tracking accuracy was only about 15 meters. It probably not applicable for construction, especially for this research. They wanted to understand more human behavior, safety behaviors, and everything, right? Yeah, so the point is the IPS, indoor positioning system, or indoor localization, still remains a big challenge. We do have a solution, but the solutions can require infrastructures and also can be expensive. That's probably why a lot of construction companies just are reluctant to do that. But for infrastructure free, we haven't developed very robust, very effective technologies yet. Okay, so that's just my personal comment. What else from the class? Anybody? All right, thank you so much, Harry. So everybody, please submit your evaluation.
Thank you, Professor.
Okay, now let me share my screen. Okay, guys. So one thing that when last week when we talk about the sensors, I just said, we're gonna have this the smart building proposal due next time. Actually, I'm wrong, guys. I'm sorry. I just missed one of the assignment, which is the smartphone app. So let me open this one. You guys can see my screen, right?
Yes.
According to the syllabus, actually the next group assignment due is the smartphone app, which I will be talking today. But because we only got 1 week for you guys, we are running a little bit behind the schedule. So I'm thinking to push this homework deadline to October 14, which is 2 weeks from today. That will give you guys enough time to develop the app as well as writing a document for that. Is that okay?
Yes, Professor.
Okay, so
14th
once
was
again,
good.
for the homework assignment 2, group assignment, we will be moving that from October 7th to October 14th, all right? But this smart building design, I think you guys should have enough knowledge to do that. So we will still stick to the original schedule. That's October 21st. All right, so let's finish the sensor. Last time we talked about, the general principles of sensors, and for civil engineering, we use sensors for buildings and structure monitoring. We talk about, different type of sensors. We talk about the definition, and we also went over the major sensors that could be used in civil engineering and construction, and also their principles, if you recall, accelerometers, gyro, vibrometers, the Doppler vibrometers, motion sensors using the microwave or infrared light, and more motion sensors, and also like using the Wi-Fi radio. We also talk about some applications of that, and ultrasonic ranger to tell the depths, the sound sensors, light sensors, infrared light sensors, temperature sensors, magnetic carbon dioxide, and also this is the one that we left last time. We actually have the laser method, and also we have this Beer-Lambert law that when the particles contained in the liquid are different, it will basically change the absorption of light, the behaviors of that. So by checking the absorption of certain frequency of light, we can tell how many particles in that. And the particle sensors are very important. So what is a particle? Basically just a mix of solid particles and liquid droplets. So not only the solid, but it can also be liquid droplets found in the air. So that's what we call particles. That's the definition. Things can be like a dust, dirt, smoke, and they are probably they are too small, or maybe they are invisible, so we cannot see them from the naked eyes. But they can they can create damage to the health of people. So this is actually a comparison chart. This is a human hair, and the size of that diameter that is 50 to 70 microns in diameter. And this blue ball actually shows the PM10, and those red balls shows PM 2.5. The 10 or 2.5, they are actually the size of the particles. So we may say PM10, that means the diameter is 10 macrons, and 2.5 means 2.5 macrons. So which means we can fit about that's actually more than 4 of that. So but the diameter of 1 PM10 can fit 4 PM 2.5. Because they are so small, they are not just hurting your respiratory system, but also they can go into your blood, and they can go from the blood to any organs in your body. So that's really harmful. So talking about that, the particle sensors, for environmental engineering, for civil engineering, that's all something we need to carefully consider. And according to the EPA definition, we have the primary particles and the secondary particles. Primary particles means the particles directly emitted from the source. For example, you are building a project and you are generating a lot of dust, or if you are burning the forest, like what's happening in California, and those particles directly from the source are called primary particles. But we also have secondary particles. Basically, that means the primary particles had some chemical reaction and generated some additional particles. For example, like the emission from the power plants, they have some sulfur, and they basically had some reaction in with the air particle. Usually, the secondary particles pose more damage and pose more danger than the primary particles, and we need to be more careful about the secondary particles. According to EPA, they regulate inhalable particles, everything that is smaller than 10 micrometers. But if that is bigger than 10 micrometers, such as sand or the large dust, so they are not regulated by EPA. So they only manage those smaller. And also we discussed that, you know, the reason we care about the particles is mainly environmental and health related. Some small particles can definitely hurt your immune system, can hurt your different kind of organs, different systems. And I also mentioned that the way we check the particles is using, a lot of times using the laser, and also showed you guys the sensor I have in my office. This little gap, if you remember, actually can track the carbon dioxide. One thing I didn't show is this system can also connect to my phone, and it can basically document the log of my, you know, 24 hours or 30 days, you know, difference. So it's actually a very convenient piece of sensor. All right. So that's basically what we could have in a building. We could have, you know, this is actually a smart home. We could have the smoke detectors, movement detectors. That's the infrared light based. You know, a lot of homes today, they have the security system. They're using that. The fall detector, that's human carrier sensors. Okay, that's HCS. Body carrier sensors, BCS. Flood detectors, sound, environmental control. Let me see what else. Carbon dioxide, carbon monoxide detector. Let me see what else. Temperature, natural gas detector, pressure mat. So this can also tell the occupant behavior. Last year for the smart building proposal project, one team actually designed. They were not doing that, but they just designed that some very cheap pressure sensors, and they basically added to the mat in front of each classroom. So you use that to count how many students went into the classroom and went out. And that can be used for us to check the usage of the classroom, so we can better allocate the resources. Maybe some rooms are more popular, so we can basically reschedule the classes or reschedule the lab hours to balance the requirements, the needs, okay? So that's just to give you some example. And also I found some interesting study called the self-powered sensors. Because a lot of sensors require energy, right? So you need the energy to run it. But like, for example, this project, they developed some power harvest system. So think about that, guys. You are using sensors to monitor the physical parameters. A lot of physical parameters, such as sound, such as light, they also carry energy. So what if your sensor can harvest that energy embedded in the physical signals that it is capturing, as well as analyzing the signal? That's called a self-powered sensors. It's actually a very popular concept today. I'm just going to play some quick video here. Share launched. You guys can still see the screen, right? For example, this is a Bluetooth-based temperature sensor. So it actually captures the energy from the Bluetooth, as well as reading and using the Bluetooth as the channel to receive and send signal. And I think I saw another fairly interesting one.
Towards much thinner and
Oh, this is
flexible.
actually a very long
Our
video,
evaluation showed
but
an
the concept
increased
is actually very
accuracy
simple.
from
They want to use
8%
this.
accuracy.
They want to use this sensor, for example, in this case, they want to use this sensor to tell if this person take the medicine as scheduled. So this is actually an infrared light sensor. It checks the not infrared, sorry. This is the light resistor sensor. It checks the luminance of the environment. But think about that light is a kind of energy. So it captures that energy while use that detects the light, but also use that energy to send and receive signal. And this is the same thing, it captures the light energy from the environment to tell, how full the cup is.
Opticians can also detect walking activity.
This walking activity, once again, this is also capturing the light, the energy in the light, while just checking how the swing of the arms blocking the light and to tell how many steps you're walking. That's one example. And this is also the stretchable sensors. They build this RFID sensor into this material. And think about that when you are moving, let's say if we build this one as part of your shirt, and when you are moving, the kinematics also represent energy. So if we can capture that energy and power the RFID sensor, that's also self-powered sensor. All right, so that's actually the most common sensors. So the challenge time, which is your third homework, is to develop a sensing solution or smart sensor network for the whale hall. Design, I'm just talking about the design of that. So I'm not asking you to buy the device, the hardware to build the sensors, but just a proposal, okay? And also you need to give a rough estimate of the installation and the development cost. So we care about the dollars. We also care about the function. So just focus on two things, function as well as the cost. So let me show you a quick example from last year, but I need to stop sharing my screen. Let me find if I can see any example. Yes. Okay, so once again, I just randomly selected an example. I'm not saying this is the best one, but I just give you a quick view of how they presented that. They basically say the problem of whale hall is and their solution. And they talk about the sensors they wanted to use. For this team, they didn't try to invent a new solution. They just basically examined what available solutions are and just try to analyze, if we want to add this wayfinding system to whale hall, because people often got lost in whale hall. And just basically evaluate that and just talk through that how the cost look like, and they give different options. Like for example, this is the smart lock data that can smart lock that can provide data about the occupancy. So basically, just went over that kind of sensors, and this is their proposal. Actually, you guys are not required to write a proposal like this. A presentation would be working, but this team actually were very serious, and they basically prepared this proposal as well. They just talk through the requirements, the alternation function, the material cost, installation costs, and different options. Okay, and I also gave some screenshots. And once again, you are only required to prepare this presentation, not this proposal. But this team prepared that because I remember they were militaries, and they just needed to present this one to their officers as well. Okay, so that is the sensor one. Now let's keep talking about the sensors, mouth sensors, all right? So those sensors, we call them embedded sensors that captures the physical signals. We also have some image-based sensors, especially the barcode and also RFID. Since RFID is so important to construction, we will just spend more time to talk about the technical details of that. So this is barcode. I don't know how many of you are using the barcode reader. Actually, if I use an iPhone, the latest iOS allows you to just open the camera and just point it and it can read that. So if you if you scan this barcode, I suggest you guys to do it now. Just scan the barcode. This is actually my personal contact information. Instead of me telling you my email address, phone number, you just scan this one with your phone. It will build a contact information in your phone automatically. So I know that this is actually very popular, the use of barcode. But what is the origin of that? Why it's working? What is the principles of that? So barcode is an optical machine readable representation of data related to the object to which it's attached. So it's nothing but imagine this is kind of like the Morse code for machine to see data. And we follow the same standard so we can interpret that or translate that into the data like text or numbers. But we have so many different barcodes, and that means we have different standards for them. Okay, so I'm just basically showing certain examples on my screen. But what is the original barcode? Very interesting story. This guy, Bernard, he was an undergraduate student at Drexel University in Phoenix, not Phoenix, what's that country? What's the name of the city? Did I pronounce it right? Drexel? Philadelphia. Anybody, did I pronounce it correct? Drexel University, right?
Yeah, Drexel.
Drexel University in Philadelphia?
Mm-hmm.
Okay. All right, so this is, he was a undergraduate student at that time. And one day, his professor invited a guest speaker to the class. It's a manager from a local grocery store. And that manager was talking about how difficult it was for them to check out the staffs. So he was thinking about, okay, so that might be a good business. So he started to think about how they could create some kind of a computer system to make the checking out faster. Then he was talking to his friend, Norman Woodland, at that time. So at that time, this guy was a graduate student, and I just convinced him this is a good idea. And guess what happened? This guy quit. But he just continued doing his degree, but he convinced this guy to quit and focus on this technology development. So anyway, this guy was from Florida. So he quit his degree and went back to the apartment in Florida. And at that time, his father was working on something, the film. I don't know if you know, for the old film, and there's something called a sound track. I don't know if I can find some image for you guys. Sound track. I cannot see that. So basically, for the old film, like this one, it includes not only the images of each frame, but also underneath that you also install the soundtrack information of it, kind of like some coding system. So when you play it, it's not only playing the image, but also playing the sound. I really want to find something. Soundtrack on film. Yes, seems like this. Okay, so this is actually the old film that they documents the sound in this way, and they have a way to translate that to the sound. They have a reader for that. So anyway, the Norman's father, was a big fan of that, and he was using a lot of such old films at home, and he was inspired by that. He was thinking, okay, so why don't we store the information as some code system, like Morse code, and we have a device. This is imagery based to read them and translate that into numbers and letters. So he just directly used the international Morse code and developed this device to read the information from the Morse code. This is kind of like what the old soundtrack on the film. And he filed this patent with Silver together in 1949, classifying apparatus and method. And this is the original figures from there, just to show how you should design the codes and how you can interpret the numbers. So the patent was issued in 1952, so about 3-year evaluation. And they went to IBM, tried to sell this to IBM. IBM didn't offer a good price. And finally, Philco and RCA purchased this patent. So that was around the 1950s. And this is the original one, like, this is the codes, and you have this device to read it and translate it into numbers. And the patent was defined, as the narrow or wide bars with a space between them. So the machine can differentiate each bars. And around the same time, David Collins at MIT was actually developing some concept very similar called a car track. This is for the railway companies. So they were trying to do the maintenance, but they just didn't want to manually document the maintenance logs of the railroad. So they just they provided a research funding to David Collins, and he developed this kind of a barcode system with blue, gray, and red colors. And of course, different combinations of that, but this is a color-based barcode reading system. But he didn't file patent, and it was only designed for a very specific application, which is the railroad maintenance. So this car track didn't become the barcode system today, not famous anyway. And so after this, Norman and Silver sold this patent to Philco and RCA. For about 10 years, nothing changed, nothing significant. But in 1966, the National Association of Food Chain, NFC, they held a meeting and they started to discuss the idea of automated checkout system. So RCA purchased, the rights to the original Woodlands patent and attended the meeting. And so they say, hey, we have this idea using the Morse code to document the numbers. Why don't we start an internal project within our association and see if we can do something to automate the checkout system, the checkout process. And Kroger volunteered to be the test bed for that. So they actually started testing that. So that is actually already in 1974. So this is actually the first barcode system used by the Kroger, and this one is called the UPC, Universal Product Code. So the barcode developed by Norman and Silver was just a technology, but like I said, we still need to somehow project the numbers you read from the barcode into some kind of a classification system. So that is UPC, Universal Product Code. And so it was established in the mid-1970s, 1974. They established this U.S. supermarket ad hoc committee to develop this uniform code. And they also signed this consulting contracts with McKinsey, and they developed this standardized 11-digit code system to identify any product, and we are still using them. So anything that you are checking out today from any grocery market, we are still using that. And this is the first use of that. It's June 26, 1974. All right. So what happened? What changed after the barcode was used in the grocery industry? So they performed the economic study and they found out, they projected that just in the mid 1970s, the entire industry saved more than $40 million by using the scanning technology. $40 million at that time is probably, I don't know, maybe $120 million now. And it's only for a couple of years. And also they saw greater responsiveness to customer needs. Just after 5 weeks, 5 weeks after using the barcode scanners, they found actually the sales just increased by about 10 to 12% and stay there, very stable. There are also 1 to 2% decrease in operating cost. And also they showed the return on investment of using barcode was around 41.5%. And by 1980, only about 6 years after the establishment of UPC standard and the barcode system, so about 8,000 stores converted using barcode scanner on a yearly basis. And now it's everywhere. Okay, so this is actually how it looks like. In general, the barcode has, the one-dimensional code. Also, today we also have the two-dimensional code. The one-dimensional code means you are only reading information in one direction, but the two-dimensional code, such as QR code, you can read information in 2 directions, which means potentially it can store more information. All right. And also original old challenge of the barcode is we need really good resolution. So originally the barcode was fairly big, so you have enough resolution to read the information. And they also recommend the use of the special barcode printer like this. The barcode printer can print like very high resolution barcode, so we can shrink the size of the barcode. But there's a standard, given by UPC that how small you can do it, usually just a 1/8 inch square. Okay, so this is how it looks like. This is the UPC barcode, or the one-dimension barcode that is used by the grocery stores today. You have the quiet zoom. The quiet zoom is more kind of like a benchmarking point for the machine to know this will be the beginning. And this is star. This is the beginning of my read. And you have this left number digits. You have 10 of them. And divided by the middle, you have another 10 digits called the right numerical digits. And the end of that, and also the quiet zone again. So if you mathematically calculate the possible combination of numbers, you could run 1 billion possible combinations, okay? And nowadays, is this the organization, the GS1 organization controls the entire standard and assignment of barcode. So why we need to assign barcode? Because if you are a chain store, if you want to use the barcode, you have to apply the barcode from this organization. It's kind of like if you want to develop a website, you need the IP address, you have to apply the IP address from the organization. So nobody, not 2 people are using the same address. Same thing for barcode. They're assigning the barcode to the companies, to the grocery stores. You have to become a member and apply for it. So this is the organization that's doing that. All right, and how it works. So basically for this one, it's a 12 digits long. And for the first 6 to 10 digits, we call this company prefix. It's basically the numbers to show the company. For example, if it's Walmart, if it is Publix, if this is Kroger, and each company will have their unique number, and you can check their unique number on this website. Okay, you just basically check it. This is how you get the barcode. You need to apply for this, and you can check. Just type in the name and find their barcode. and then the rest will become the atom number. So what do you see, like say you're back saying from the publics, if you check next time, not public, sorry, for example, you buy Coke products. If you check next time, the first couple of digits, they might be identical, they might be the same. It shows that, oh, this product's from Coca-Cola company, and the rest will be different. That's actually internal. Like Coca-Cola can, the company can decide what number they assign to the stack Coke, what number they assign to the zero Coke, but the first couple of digits should be applied and assigned by the GS1 organization. All right, so that's the UPC standard. QR code is also, it's probably more popular than the one-dimensional UPC code. QR code full name is called Quick Response Code. Originally, it was developed, patented, and owned by Toyota, a subsidiary company of Toyota called Denso Wave, and originally designed for the car parts management. But fortunately, this company decided not to exercise their patent right. So they basically made it free to everybody. So that's why the barcode now is so popular. You can pretty much store any kind of information there. Of course, we have an international standard called ISO IEC 18004. In fact, everybody can just use it for free. Just basically search QR code generator. Google used to have this website, but for some reason they give it up. But we have this QR generator. So you can store any information. For example, I just want to store my cell phone number. Okay, so I just type in the number here. You see the barcode is changing, and if you use your phone to scan it, and automatically it will basically show. I don't know if you can see my phone. It basically shows the number automatically. So it's kind of like a coding decoding system, very convenient. And of course, you can exchange message like, where do you want to have dinner tonight? Anyway, it's a barcode, and so you just scan this. And it shows the text, where do you want to have dinner tonight? So since they gave up on their patent, that's why there's so many free online tools. You can generate your barcode, print out, and do whatever you want, okay? Sorry, not barcode, QR code. And this is how it looks like. This is the configuration of that. We have this, the general format required patent is this 4x4 pixel. So matrix. So basically, if you see here, you see this 4x4, that is one information unit, 4x4, one information unit. That's how the QR code reader interpret the information, the basic unit that how it interpret the information from. And we have the three things to define the position. So this one is more kind of like how the computer can know what is up, what is down. That's why to read the barcode, you do not necessarily to put it like in the same way. You can basically, if you rotate your phone like this and just read it from any direction, it still give you the same information because we have the anchoring points for the machine to understand that. This is the alignment. Okay, so for each one we have three, for each, let's say, chunks of information, we have three position code. We have this 6 alignment code, and we have the quiet zoom. The quiet zoom is more kind of like knowing, let the machine know, okay, now we are entering this zone of reading information. And also it shows the format information, for different QR code, they read this piece of information to know what is the particular QR code information I'm reading. Version information, QR code now also have different versions. So they read this number and the machine understand, oh, I'm reading this version 1 or I'm reading this version 2. And also we have this data and error correction key. So what I mean, basically it shows that, if any of the QR code is damaged or let's say dirty, and then the scan will meet some error, but they develop some very smart mathematical functions. So for example, this number is the addition of some number here. I'm just giving an example. It's not the case, but it's very similar. then, even though some information is missing, they can basically come here and check to validate if the information I read from here is correct. If anything's inconsistent, then the machine knows something's wrong with the QR code. So this will help you prevent from having the wrong information from the QR code when it's damaged. UPC actually uses a similar concept. I think one slide actually showed that. Yeah, so here, for example, this UPC, I forgot to talk about that. The last digit in UPC is a check digit calculated from the previous 11 digits. That's why you have 12 digits, but I can only use 11 digits. It is not randomly assigned. It actually, there's a formula built in that can, based on the formula, they check, they cross-validate if the previous 11 digit makes sense or not. Let me see if we can find it. UPC 12 digit. Let me see. Check digit. Yeah, this is also standard given by the GS1. I don't know if they show the formula. Yes, manually. Yeah, so this is the formula given different format. It just shows how you multiply the value of certain digit, let's multiply 3, multiply 1, and add them together, sum, and you got this digit. And if anything's wrong, for example, something blocked and damaged, and then they basically cross-check and something's wrong, they know this is damaged. So this is just a quality control method, a very smart design. And similarly for the QR code, it also has this kind of a quality control method. And this is how the machine reads it. Basically just start from one direction, from one place, and just keep going and read this formatting information, then keep going and just to read each of the units and just doing this kind of circle until it finish all the reading and translate that into the useful information. And you can see the bundles, a QR code could have, multiple, I don't know how them blocks, okay? So for each block, you have the, the position and you have the alignment code. So this, you still have the 3 positions. So this one helps the machine, the reader, to know which is up, which is down. But then you see this one, just see how many alignment code you have. So this is really big. And for one barcode, you can only store about 20 to 30 characters. Each character is about 7 bits. But 2D code can go up to 2000. So you can actually store a short message. So I'm just going to scan this myself. All right, and I write it. So this is the text, stored in this QR code. You can definitely play it yourself. Talking about a reader, yeah, we do have the barcode scanner and the professional readers, but nowadays smartphone can do that. This is kind outdated, but they are expensive. Yeah, like the reader can cost you $200, $300 to $500, $600, $700. Yeah. Okay, so yeah, you guys, I guess, you can definitely play. You just Google free QR code generator online, and you can try different things. Somebody asked me, will we use all the QR code? I guess the answer is no, because there's so many different combinations. And if we're running, actually, I don't think it's possible to use all the possible combinations. If so, we can still, develop a new, we can still keep adding the blocks and make the QR code store more information. And we can also develop strategies to erase the previous information. But to answer that simple, it's impossible. to use all the QR code combination. So that's the barcode and QR code. We will talk about why it can be useful in construction. But another or similar or comparable technology that a construction can benefit from is the RFID, okay? So the RFID stands for radio frequency identification. It's a technology using the radio waves to identify the object. So basically you have this RFID tag with a microchip built in. So the microchip is the brain of RFID tag. It stores the information like ID information or location information. You also have this RFID reader that reads that information from the chip, right, the microchip. You also have the middleware, which is the server to receive and process and store the information. And in general, RFID has two kinds of technology, passive RFID and active RFID. The passive RFID, you do not need to provide a battery. You do not need to provide a power. Basically, it's died, it's inactive when you are not reading it. But when you read it, you are sending energy to it, and it sends back the data. But active is self-powered. You're usually hooked up with a battery. So what are the different pros and cons? So for active RFID, of course, battery will be needed, but for passive, no internal power will be needed. And the signal strength, required signal strength means the reader strength. So basically you have the reader, you need to read the information from RFID. Because active RFID, you have it's powered, so you just need a very low energy reader to read the information. But for passive RFID, since you have to activate that first, you have to send the power to it to activate the chips. So the power required for the reader will be relatively high. And similarly, passive RFID, since there's no internal power, the range of that is very small. It's around 3 meters. But for active RFID, it can be more than 100 meters. And also similarly, because the more data is stored in the microchips, the more power you will need to for the bandwidth and also for the storage. So for passive RFID, you can only store about 128 to 256 bytes of data. But for the active RFID, you can store 32 to 128 key byte of data. One key is actually 1024 bytes of data, right? So this is much more than the passive RFID. The tax, of course, for passive RFID is very cheap, about 10 cents to $5. But active RFID, since it has a better microchip and also the power system, so it's around $15 to $100 each. The size, usually for the passive RFID, we are talking about the sticker. For example, like the toll road. This is actually the Texas toll road RFID tag, and also in Florida, we also have a similar tag. This is actually RFID. It's a passive RFID. Okay. But for the active RFID, the size can vary depending on the application. Talking about the fixed infrastructure cost, because the active RFID has its own system for information storing and sending and receiving. So the reader system, the system to read the information can be cheaper. But for the passive RFID, you do need a better system to read the information. For example, for the toll road, when you're driving this car to the toll road with RFID, you see that the gate is actually equipped with really good sensors and readers to read information from your RFID. So that is actually more expensive from the reader end. And also the area of use, for the active RFID. So we are talking about, the assets moving within a designated area. But for the passive RFID, you can imagine it's kind of like all the objects going through a gate. So you can imagine the passive RFID perfect example is the toll road. It's actually the sticker put on your car. But the active RFID, you can imagine something hooked up to the construction equipment. So you can track how it's moving on the construction job site. In terms of industry, passive RFID heavily used in the supply chain, the high volume manufacturing, bookstores, passports, tours, atom level tracking, but for the active RFID, we are talking about auto manufacturing, hospitals, asset tracking, construction use that a lot, and IT remote monitoring, okay? This is actually how it looks like for the passive RFID. You know, you see this is, this is the microchip, and you have this antenna, okay? And this is the substrate that is hosting everyone. So just a chip plus the antenna. That's very simple structure. And also for a lot of what do we call the chip card today, it also just a chip built-in that stores the information, and also a built-in antenna to amplify the signal. Actually, the tag, the Toro tag used in Florida is very smart. It used the windshield as the antenna. That's why when you paste it to your car, you have to make sure it's leveled and have good contact with your windshield, because it uses the entire windshield as the antenna to read the reader power and also the information from the power and send out from the reader, and also send out the information to the reader. So what is the origin of that RFID? I think I shared the story. This is he was a very smart, amazing engineer, Leon Sirman. He developed the first passive RFID called the Thing, but this thing was used for spying. It was a bug. So let me show you the story.
What was the Thing? The Cold War. This episode is brought to you by Dashlane. On August 4th, 1945, a group of Russian schoolchildren from the Vladimir Lenin All-Union Pioneer Organization presented a 2-foot wooden replica of the Great Seal of the United States to the U.S. ambassador to the Soviet Union, Avril Harriman. Believing it to be a mere friendly gesture of friendship between the USSR and the USA as allies in World War II, the Great Seal was hung up proudly on the wall of the ambassador's residential study in the library at the Residency Spaso House in Moscow. What the Americans didn't know was that this gift was holding a secret. This gift was not merely decorative. The Soviets had placed a high-frequency radio bug inside. This listening device, dubbed the Thing, enabled the Soviets to eavesdrop on confidential conversations of the U.S. ambassador. Surprisingly, the bug worked without batteries or electrical circuits. Instead, it was initiated when a radio signal aimed at its antenna from a van parked outside the building activated it. The sound waves from conversations within the office caused vibrations of the membrane inside the carving of the Great Seal, which beamed back to the surveillance van. This simplicity meant that the listening device had an almost unlimited lifespan and was difficult to detect. The Thing was on display for 7 years until it was discovered in 1952. In 1951, a British radio operator suddenly picked up a signal, accidentally overhearing American conversations while the Soviets were using the bug. The sweep didn't find anything. In fact, whenever major repairs were made to the offices, the walls were inspected for any concealment of bugs. The Great Seal was always taken away and examined, and then returned in place afterwards. A second sweep in 1952, provoked by another accidental overhearing of the ambassador's office on a radio signal, found the bug in the Great Seal. At first, the Americans were confused by the seal and didn't know if it was an actual bug because of its simplicity. But eventually, after analysis, it would lead on to a British version of the device. The discovery of the bug was kept a secret by the Americans until the U-2 incident in 1960, when the Soviets accused the Americans of spying. To show that both sides were guilty of this, the Great Seal bug was revealed during the meeting by U.S. Ambassador Henry.
And I found this documentary online.
I have a quick favor to ask. Please request a ballot today so you can vote from your home this election. Voting from home is
1960. The Great Seal bug reappeared.
At the United Nations, the Security Council debate on Soviet charges of American aggression ends with a sharp final clash between Gromyko and Lodge. Ambassador Large counters repeated denials of Soviet spy activities with a concrete and dramatic example. He tells how the Soviet planted a listening device in America's Moscow embassy, concealed inside a wooden carving of the Great Seal, presented as a gift by the Russians.
Go ahead, open it up. And here is the clandestine listening device. You can see the antenna in the area, and it was right under the beak of the eagle. I might add that it's really quite an interesting device.
For weeks, the
Yeah, so technology is no good or bad, right? So just a smart, piece of engineering product, but just anyway. So it basically promoted technology, and that's why we start to use that a lot nowadays. So talking about RFID reader, it can also be like different shapes and tabs, and also there are some devices can hook up with your phone. Actually, nowadays, each of the smartphone, most of the smartphone and also the smartwatch has this kind of RFID built in. It's nothing but just a storage of some important information like your credit card information, your address information. So whenever it tries to validate your identity, it just read the information from there, all right? And this is RFID middleware. Like I mentioned, it's kind of like a server processing the data and store the data. And this is how it works. First the reader will send a signal through the antenna. It will activate the RFID tag, either the active one or the passive one, and let the tag knows, oh, I'm about to read the information from you. Then the microchip will send out the data back to the reader. And if this is passive, and when this reader sends out this signal to activate the tag, it will also provide energy to the tag. And then the information read will basically send it to the middleware server. Very simple process. And RFID uses radio, and radio has different frequency. And we actually use a whole lot of frequency ranges for RFID today, and they have very different application scenarios. We have the low, high, ultra high frequency, and the microwave. For low frequency, the radio wave we use ranges from 100 to 500 kilohertz. The distance is short to medium distance. Cost is low. Read speed is very slow. And so this is for high frequency. We use the frequency ranges from 10 to 50 megahertz. So the range once again is short, but it's longer than the low frequency one. Cost is low. Read speed is better than this one. For ultra high frequency, this is from 850 to 950 megahertz. For microwave, that's 2.4 to 5.8 gigahertz, and the range is actually really long. And so the requirements is, the read speed is very fast, and also, but because the use of the high frequency radio wave, it must require the straight line distance, so it cannot broadcast in this way. So this one is usually used in this toll road, because we need to read the information really fast. The cars can drive really fast, so we need a ultra high frequency. And this one is usually high frequency really used for the credit card. And also the low one can be used in other, for example, like your car. The cars, the smart key that it can open or close the car doors, that's actually low frequency. Now, question for the class: why the ultra high frequency and the microwave, the read range are really long? Anybody? Anybody from class? This is physics 101.
It's because it has power.
We're talking about, it doesn't matter. It doesn't matter if it's powered, active or passive. When the radio frequency we are using for the system is ultra high to microwave, the read range will be longer. Why?
Because the length of the wave is shorter.
Exactly. I don't know if that we're on the same page, but yes. So Basically, when the frequency of any wave is higher, the energy is bigger. That's physics example 1. Make sense? So the wave, when the wave is faster or the frequency is higher, it carries more energy. And because it carries more energy, it can travel a long time. That's also why the ultra high frequency RFID or microwave can only used for straight line. You have to be able to see that. Why? Guys, I mentioned that. Because it can be easily bounced back. So if you have occlusion, like if, for example, there's a column blocking the view, then very likely the high frequency one will be bounced back. Why? I mentioned that last time. Because for high frequency wave, it behaves more like a particle. It's more like you're throwing the balls to somewhere. Yes, energy is big, but it can be easily bounced back. For low energy, it can easily penetrate things because the wave is bigger. So if the wave is bigger than the diameter of the column, it can easily travel through the column. So that's why it's more like kind of like a broadcasting, right? So that's why when you try to use the key to open your car, you do not need to point to your car. You can point to the opposite direction. You can still open the gate, the door. Make sense? So that's actually some principles you have to understand. That's how you guys can be the inventors of the new technology. Now microwave, 2.4 gigahertz, 5 gigahertz. Do these seem similar to you guys? Seem familiar to you guys? Think about the Wi-Fi router you use in your home, right? 2.0 gigahertz, 5 gigahertz, and we know what? The 5 gigahertz is usually what? The download and upload speed is usually faster using 5G, not 2.5G, right? But if your bedroom is too far away from the router, then the 5G signal will be weaker than the 2.4G. Now you understand why, right? Because 5 gigahertz is actually the frequency is even higher. It carries more energy. More energy means it can provide more bandwidth for you to upload and download data. But it behaves even more like a particle, so it can easily be blocked by the walls and doors. So that's why 2.4 gigahertz can travel through the walls. Basically, we're talking about not just walls, guys. We're talking about the studs building, the 2x4, 2x6 studs building the wall. 2.4 gigahertz can easily penetrate, or because of the frequency, the wave is bigger, so it can go bypass, the studs and go to your phone. But for the 5 gigahertz, it's probably just bounced back by the studs. Make sense? So I hope you guys now understand what it means. So basically for Wi-Fi, it's radio, and we are using microwave for Wi-Fi. Okay. Now, why barcode? Why RFID? So this is a good metaphor. The barcode scanning is kind of like you are just fishing using the bait. Okay, so because it's one-to-one, so you have to use the reader, use the camera to point to one barcode reader information. But for RFID, because this is radio and the radio broadcasts, it goes everywhere. It's possible for you to use one reader to read multiple information, information from multiple devices. This is kind of like fishing with a nest. So imagine if for your particular application, you want to read, for example, some cars that is carrying pipes and concrete, a lot of different things in the truck, and with different RFID tags. It goes through one gate. Then just like that, you have all the information read from all the RFID chips. But for barcode, you have to basically use that scan 1, scan 2, scan 3, just one by one. All right, guys. So let's take a break for 15 minutes. Let's return at 5:40. Okay, see you then.